Okay, welcome back. Okay, so there's small. Okay, there's a message chat box. So small confusion. Training set plus validation chances of no errors. Test set chances of error we can able to see it right. Okay, so idea behind the trainings and validation and test set is that the error should be less in all of them. Okay, so it is not that there's no chance of error in training set. Okay, because we are not, right now we are looking at very simple examples. So it seems that there will be 100% accuracy on the training set itself, but it is not true. Okay, in reality, the data set is they are very big. Okay, they may be in thousands or millions of samples, okay. And there is noise always. Okay, and they may not be sufficient data, enough data. Okay, the features may not be good enough. So all these different possibilities are there, due to which the training set itself is not completely classified. Okay, even if you give the training set again as a test set, if you just learn on a training set and give the same training set in a real world, you will not get 100% accuracy. Okay, even there you'll have problems because there is some noisy data. Okay, but yeah, if the data is not very complex, you might get 100% accuracy on the training set. Okay, but that is not what you are achieving. You are looking for. Okay, you are looking for accuracy, good scores on the test set. That is unseen data. Okay, and unseen data should be selected such that it represents the real world situation. Right, it should have different possibilities which are present in the real world, and then you see how good the classifier is able to classify based upon that test set. Okay, so ultimate goal is to get good score on the test set, or the best score on the test set, best possible score. Okay, so again, it will not be 100% accurate, but you want to get as good as possible on the test set. But how will you know that your result is going to be good at test set? That is by looking at by working on the training set plus validation, right? So training plus validation is train set. By working on that only, you will be able to finalize a model. Okay, so this kind of all these whatever learning is applying on the training part, training plus validation. Okay, well, let's come to the ensemble based methods. So ensemble is kind of a collection of various classifiers or collection of different models. Okay, and so this, what you do is basically you combine different decisions. Okay, so these different decisions may be decisions of different classifiers. For example, you could have one SBM classifier, one different kind of a classifier. Okay, and another. So we may have 3 classifiers, for example, and let's say they are all individually giving good results, good scores. Okay, maybe they are all giving above 80% F1 score, macro average, let's say. So when they are all individually quite strong, and you also see one more thing that you have to see is that they are giving different kind of scores. Okay, they are giving good scores, but they are not giving same kind of scores. If all of them are good, but they are all giving, let's say, in a binary classification, positive negative, and the class is positive and negative, and all of them are like giving positive to certain examples and giving a negative score to certain examples. Negative class, they are labeling positive and negative similarly. In that case, there is no difference among them, right? They are all labeling similarly. They are all classifying similarly. So in that case, it won't be helpful. Okay, but there might be cases in which the different classifiers they're classifying differently. Okay, so they are classifying different enough so that there are enough examples in which the classifiers are not agreeing. Okay, or there is a disagreement among the 3 classifiers that you are using to combine into one and creating an ensemble. Okay, when you have a disagreement, then It is important. Okay, then you might create an ensemble of classifiers from these three, which are individually all good, and they are giving different kind of scores to good enough number of examples. Okay, then you can perform something like, say, majority voting. Okay, so in majority voting, you will give that score to the sample depending on the majority. If whatever two of them are agreeing on, you will give that score to the sample. Okay. So this kind of ensembles, it might result in improved accuracy. Okay, because an individual agreeing is not as good as two strong individuals agreeing, right? So there is an agreement on two, then, or if we have, let's say, five, then if there is an agreement on at least three, then it's a good the good way to select is the majority. Okay, or the label which is selected by the majority should be the one given in the majority voting. So there's ensemble kind of methods. It's a very hot area of research, and it results in improved accuracy quite a few times. Okay, and especially when the classifiers or whatever you are using, when they are disagreeing or when they are giving different kind of results, you might combine them and create a ensemble which improves the accuracy. Okay, a real example, I'll just give you one example. So this is one example from my research that you can see. So here we have different kind of term weighting methods. So certain term weighting methods. So just like TF, IDF or term counting, there are various methods. Then you can see that let's just look at the linear SVM, that is because that is the best scorer here. So there are two classifiers that we are using, logistic regression and linear SVM. Okay, and you can see that just for linear SVM here, the individual scores are quite good. Like for example here, proposed method or the mod IQF, okay, and TF log x square, TFOR, these are found to give good scores. Okay, IQF, QF, ICF was kind of similar to mod IQF, so we didn't use it. So remember, as I mentioned earlier, individual whatever you are combining, individual classifiers, they must be disagreeing significantly. Okay, so in this case, IQF, QF, ICF, and mod IQF, they are kind of different versions of the same thing, so they were not disagreeing on enough samples. Okay, so we only selected this particular one, the proposed one, and one of either TFOR or TF log square. Okay, and then created two ensembles. One is called voting one, and one is called voting two. Okay, and you can see that the result of voting one and voting two, they are much better than any other individual scores. Okay, so these are the individual scores, and those inside the box are the scores of the two voting classifiers. There's voting on their ensembles. Okay. Right. So there's a question: why we use logistic regression? Why not linear? Sorry, I got this question when I revised. Okay. Okay. So logistic regression is kind of much better version. Okay, much better than linear regression. Okay. So linear regression is just linear. You just want to get a linear decision boundary. But in case of logistic regression, the boundary can be non-linear. Okay, it can take a lot of different shapes. So that's the basic idea. But don't worry, don't go. You can go into more detail about logistic and linear regression if you read about some machine learning books. Okay, but right now we are not discussing that. Okay, only thing is linear regression much simpler form. Okay, this for the very basic examples. Otherwise, it is not used much. Okay, logistic regression is the one that is a good classifier. It is used much. All right. So the idea here is that the ensemble based methods are improving the accuracy. So here the macro average and micro average score, you can see micro F1 and macro F1 of the ensembles of the two ensembles and particularly the second ensemble, the voting 2. So voting 2 was created out of the proposed, the mod IQF, and the TF log x square. Okay, so out of these three, we created the voting 2 classifier, and you can see that each score, either be it the micro F1 or macro F1 or linear SVM of, or maybe of from logistic regression, they're all column wise, they are among the best, or they are the best. Okay, so voting 2, for example, in linear SVM, if you look at the micro F1 score, so voting 2 has the best one, right? 0.8227 is the best score in this micro F1 for linear SVM, and for macro it is the best. And the same thing is for logistic regression. They are also giving good scores, but not as good as the SVM. So SVM is giving the best score, and it is linear SVM, that is linear kernel, something called linear kernel. So in your assignment also, you will have a similar kind of. I mentioned it. I think use linear kernel. Okay, just select kernel is equal to linear. Okay, don't worry about the detail. It just means that the decision is the boundary that is created is straight line. Okay, or a plane, or in high dimension, it's a straight kind of, it's corresponding to a straight line. Okay, so let's now. So this is about the ensembles. We're not going to detail, but there's theory behind why ensembles give good results as compared to individual. Okay, you can read more detail if you wish. Alright, so let's now come to the assignment discussion, the important one, because a lot of you have asked for clarifications and had problems in assignment. Okay, so there's a comment here. It took 1 long week to solve the clustering problem. Now that I've completed the assignment, we have increased the scope. Will not have time if I keep working on the assignment. Okay, so what I've done is I've not increased the scope. Okay, only what has been done is just the measure that you are using. Earlier I just mentioned silhouette score, okay, as a measurement, as a score to measure that internal evaluation measure silhouette. But when I wrote my own code for the assignment last night, okay, and I compared the silhouette coefficient, it's coming up to very low. Okay, and when I knew the labels, yes, the silhouette scores are very low, and even if you put all the documents in the proper clusters that I know they are from the same cluster. So what I've done basically is whatever the files are there for the classify to classify, okay, same files are there in the cluster. I just put the same files in a single folder for clustering. So even if you have 5 different clusters, you just have those 5 different classes, and each class you say is a cluster. Even if you just calculate or compute the silhouette score on the actual class labels, assuming that each label is going to its own class, different class, 5 different classes, and corrected classes, even then the silhouette score is coming out to very low. Okay, so that means it is not a good measure here. Okay, in text, in our document cases. Okay, maybe 0.1, 0.01, something like that, right? So it's better to use other method. Okay, I'll explain today what you have to do. Don't worry, it's very small, 1 or 2 lines of changes. You don't have to do a lot of different things. If you have done so far, it won't be more than an hour or 2 of work. Okay, so let us discuss the first problem about the classification. Okay, so in this there were 5 different folders. Okay, and each folder has 50 email documents. That means 5 folders, total 250 documents are there. Okay, and then same 250 documents have been send. I put in the cluster also. Same. Only thing is that in the clustering I didn't put the 5 folders. All the files, 250 files together I put cluster in the cluster.zip without any further hierarchy. While in case of classification, 5 folders, and each folder I have 50 files. Total 250. Okay. Now in this you have 50 image documents, assuming that the document in one class, the classifier should be able to tell the difference between document in one class from the document in other class. Okay, from the document in other class. Okay. So I asked you to create a decision tree classifier and a support vector machine SVC classifier, which is in the these are all available in the sklearn library. Okay, and then is the score you report micro average and macro average F1 score of 10-fold cross validation. You may need to pre-process the data, prune the decision tree, and find good C values for SVC. Okay, and then you have to submit a table, macro average, the macro average, F1 score, and Python code. Okay, there is a question: can we submit my code in Jupyter Notebook format, or should it be Python only? No, submit on Python only. Okay, whatever is mentioned, just submit that. Don't submit me Jupyter Notebook. Okay, so there are questions. Some of you are not able to see how, or not able to figure out how to use those folders. Okay, how to label, how to put the labels on those files. So here's almost completing what you have to do. So this can be used. This code can be used by both cluster and classification. Okay, both the problems can use this code. So basically, there's a OS. I think we have used this earlier. The OS module. Okay, so this OS dot list dir. So this is the function. If you give any path, it will just list all the files and directories in that particular folder. Okay, so in this particular directory, give the path to that directory, and remember there is a slash at the end of path. When you concatenate, it will be useful. Okay, or you can just create a string with this file and then just use the string. That is better. Okay, so what you will do is just go to that directory, the top level directory, to classify, the path to that directory called to classify, right? And then within that, look at all the directories. So again, for fin, so this code what is doing is looking at all the files inside every such directory. So inside classify you have 5 directories. So for fin, so it will look at each directory one by one. So D is taking value. So D is the directory, one of the 5 directories. So we'll go into first directory, look at all the files in that directory, and append the full name of the file to a file list, F list. Okay, so F list is a list that you have to declare earlier, and will append the whole path to each file in the F list. Okay, and at the same time for each file, it will also append the name of the directory D. Okay, so D could be RA or whatever small names you had, right? 5 directory names you had. So here I am using those name of the directory itself as a label. Okay, so remember you have 250, a list of 250 files, F list. Okay, and Y will have the corresponding labels, right? So the first 50, let's say they belong to some class, let's say RA. I don't know, I don't remember the names. Let's say RA. So first 50 will have labels RA. So this will have, you'll have the corresponding X and Y values. Yeah. So if CW, okay, so if the first label is, let's say CWX, okay, CWX folder. So Y dot append will be CWX. So this is thing called CWX will be appended to Y 50 times. So these are first 50 labels. Okay, if the first 50 files are from this folder CWX. Okay, so now you are getting file names, full file names, including the path and their labels in the same order, right? So you get 2 lists, the list of files, F list, and the labels for those files, right? Now once you have list, once you have labels, corresponding labels, it's very easy to perform classification. Right now, some of you are having problem with some problem with when you perform the TF-IDF transformation. Right. So for that, there's a problem with this particular thing is the encoding. Okay. So if you use encoding is equal to Latin 1, it will be fixed. So just use encoding is equal to Latin 1. It won't show any problem. There's some encoding problem is there. UTF-8 and all this. Okay. So the objective is, okay, there's a question. Objective is if I provide new email, it should assign any of these labels. Yes, that is the objective of a classifier. Okay, ultimate objective should be like that. But here you are not doing any of this. What you are doing is just cross validation. Okay. Okay. So if you pre-process the data, then might not have the problem. So just pre-process the data early. Then you will not get error. Okay, if you are not getting any error, then don't do encoding. If you are getting error, then you should put encoding is equal to Latin 1. All right. So this TF-IDF vectorizer. Okay, one more thing. Now what you want to do is, instead of the example that we have seen in earlier contact hours of count vectorizer and TF-IDF vectorizer, what we gave was strings, right? We gave the strings itself here. But now what you want to do is you want to give it a list of file names, and you want to tell it, okay, I want to create vectorizer for these files, or you want to vectorize these files, each file as a document. Okay, so instead of a string as a document, what you want to do here is each file, you are looking at the content of each file as a document, and for each file you want to create a vector, the term document matrix. Okay, so here the document is a complete file. So for that, the input should be given as input is equal to file name. Okay, input is equal to file name inside single quote. Okay, so input is equal to file name. This will be this, and then you perform that vec dot fit underscore transform, and you give the list of file name. F list you have to give when you transform fit transform F list. Inside that you give F list, and then I have written fill the remaining code. So here you will have to use stopwatch is equal to English. Just look at the API. We look at the sklearn. Go to sklearn page for TF-IDF vectorizer. You will see different possibilities. So use stopwatch. You want to remove stopwatch. And also there is one more important thing. Just look at min df. Okay, min underscore df. So in how many documents should a term be present at least, so that it is important. Okay, so just use a few. Let's try 2, 3, 4, and see which is giving you the best score finally, and select the one that gives you the best score. Min underscore df. Okay, so that's the remaining part that you have to fill up. So apart from min underscore df and stopwatch is equal to English, I think that will be all. Okay, just try it out. Now there's a question. So we'll have 250 rows. 250 rows, yes, or in the matrix, in the term document matrix, 250 rows or 250 files, and each row will have complete vocabulary set. Yes, it may be thousands of them, maybe 10,000, 20,000, like that. Okay. But if you use min underscore df, if you increase that, the number of vocabulary will decrease. Okay. Yes. So that's why min df we use normally 2 or 3, not more than that. Okay. Unless you have a vast number of data. Here you don't have enough data. You are only using 50 samples in each. So maybe you can only select min underscore df is equal to 2. Okay. Because if a term is in only one document, in only one file, then it's not important. So use min df is equal to 2 or maybe 3. Try 2 and 3 and see. Okay, so one of them will work well. Okay, but okay, there's a question. But increasing min underscore df will reduce f1. No. Okay, it might make it better, but not always. Okay, it will increase and then decrease most likely. If it doesn't increase, then don't do it. If it improves, look at what is the best value for min df. Use that value. Okay. Okay, so there's a question. We will use fit, then TF IDF, and then finally cross validation. No, you will not use fit. You only use. You can just directly use fit underscore transform. Okay. After calling this TF IDF vectorizer this function, defining this vec, then just call vec dot fit underscore transform on the list of files. Okay. Okay. So I'm not describing about porter stemming and all that you have to do as a part of pre-processing. So just go to individual file and perform porter stemming and all. But the stop words removal you can do here. Alright, so try this out. Alright, so this is the main thing. Apart of once you create the vectors, the term document matrix is created, then you can use the function called cross underscore validation underscore score. Okay, so this is the function that can. So before this you have to declare a classifier. Okay, classifier with proper arguments. For example, in case of decision tree, you have to set the number of min number of nodes required to split or the height of the tree. So try with all those different combinations. Okay, so decision tree you have called, let's call it CLF. So that CLF you have to give to cross validation score, cross val score, this function. Okay, so because I have asked for 10-fold cross validation, so the cross validation score will take CV is equal to 10 at the end. Can use CV is equal to 10, and other arguments we'll figure out. Okay, first argument will be the classifier name. Let's call it CLF, and then maybe X and Y. Just try it out. So CLF is the classifier that you have created. So you don't have to fit here. Okay, don't call fit because the cross validation score itself is doing it for you. It is just dividing that data of X into 10 stratified groups or 10 folds, and then it will automatically perform cross validation for you and report the score for each fold. So here print cross validation score will give score for 10 folds. If we see is 10. Okay, if we want to get the average of those 10, we can also use np.mean. This is the average of those 10 folds. So the output will be something like this. When I run on SVC without performing any porter stemming and all, this was the score for the 10 folds. So you can see that in 2 folds you get 100% accuracy. Okay, and the average score was 0.94. Average for the 10 folds was 0.94, which is quite high, even without doing porter stemming. So you should be getting better score than 0.94 on average. Okay, Nagabhushanam. Graph.render Bice computer. Which code are you talking about? Bice computer. Okay, you are getting some error. But I think we discussed in the class. I saw the live demo, so it's not any problem. Okay, see some double quotes, single quotes, maybe some problem. Okay, anyway, we are discussing the assignment here, so maybe this will discuss in the review session. Okay, so this is a score for F1 micro. So the micro F1 score, micro average score. You can also use the macro average score. Okay, so ultimately what it is doing is, okay, one of you asked where it is not, it is just 5 classes, right? So how it is doing that? How it is performing the classification? Because in binary case it is fine, but when it is 5 classes, right? We have 5 classes, and how it's performing the classification, each classifier. So what is happening is that here you have 5 classes. Let's say C1, C2. So there are 5 folders. Okay, let's say there are 5 classes corresponding to those 5 folders. Okay, C1, C2. So what it does is it performs binary classification only, but it performs it 5 times. Okay, so what it does is each time it will take one of these classes positive and all the remaining as negative. Okay, that is one. Then second time it will do C2 second class as positive and the remaining all as negative. So we'll do that 5 times. Okay, and the micro average and macro average then calculated based upon these 5 different times. Okay, so here, for example, in this particular example, when the first fold is showing 0.87 as micro F1 score, micro averaged F1 score, what it means is that it is performing those 5 times 5 classes are taken as positive. Let's say in the first case the class 1 is positive, remaining are all negative. These are all negative, and this is positive. Okay, so what is the score there? What is the TP? What is FN, TN, all these things? FP, TP, FP, and FN. All these are important, and based upon that, it is calculating F1 micro, okay, for each individual. So in the second fold, it will take the second X positive, remaining at negative. Okay, so it's called one versus rest. So internally, it is doing one versus rest inside the sklearn library. Now in assignment, I've not asked you to plot the decision tree. Okay, so just read what I've asked, only do that part. Okay, so this is about the classifier. Now the clustering problem is this. So this is the original problem. So you know what I had done is, the original was I put in the cluster to cluster.zip folder, I put 250 files all together. Okay, now I removed that file. Instead of what I'm doing is now I'm just creating. We are using the same to classify. Okay, so we can see that your initial code for putting them into particular classes and labels is all same. Okay, so you'll again create the file list and while list, and also the TF-ID vector is also same. Until here the same code. Now the code is common until here. Okay, but now what is important here is now you have got the actual labels. So why is the actual labels of those 250 files? Okay, and now once you have the actual labels of those files or those documents, then you can compare your clusters against the actual labels, right? That is what we do in external evaluation measures. Okay, so in this case, they are giving better score than the Slovak. So in this, what we'll do is, so instead of the single Slovak score, we'll call something like adjusted rand score. So here, even though it looks complicated, you have 4 or 5 scores, but only difference in the call when you call those functions is the name of the function. Okay, the arguments are same. So whether it is adjusted rand score, whether it is normalized homogeneity score, all things. The arguments are all y comma lab. So y is the actual labels and lab is the labels that you are getting. Okay, so you can remember, you can see that CLS dot labels underscore, right? In the class also we saw this. This will show you the labels, in which label it is putting. If you are putting, if you are getting say 5, or let's say you have created 8 clusters. So I have asked you to tell it how many clusters you want. So if you are putting into 8 clusters, then we'll have 8 labels. Okay, and then we'll compare those labels with the original y and see and find these different scores, adjusted rand score or other scores. So these are the different scores that you use. So adjusted rand score, the v underscore measure score, completeness score. Okay. So I've not discussed all these scores, but they're all kind of external measures to measure the goodness of clustering. Okay. So I think you have to import this, and I have shown the example of. I think I've shown this example. You can just search for this, in which module these functions are available. So those most likely they'll be available in sklearn.metrics. So from sklearn.metrics import adjusted rand score comma v score, v measure score comma this. Okay, and then just call them, and you see that for certain number of clusters they will all be maximum. Okay, so I tried it all, and without any pre-processing. Remember, so even then I'm getting good enough score. So this was kind of maximum for all these. So they are all increasing and decreasing kind of in a similar way. So they are all either decreasing or increasing for different values of k. So they are all good measures, you can say. Okay, now there's a question, but in reality we will not know y values for clustering. Yes, you might not know. True, but what happens is that when you create clustering methods, you normally should know the label so that you know, okay, how good your cluster is performing. Okay, so there's because the algorithm is common, right? There's the same method whether we have class known or not known. So why not just use some data set in which you have the classes as known and then compare against them. That is external evaluation measures. Okay, and you'll see that is a very popular way of doing clustering. Okay. Almost all the research when they perform like this. Otherwise, there is no way of knowing how good the clustering is. Okay, silhouette score alone is not sufficient, like we saw in this case. In case of documents, especially. Okay, but once you know, okay, but what you can do is once you know from the known labeled cluster that this you are getting a good score, then you can use this on unseen, unlabeled data. Okay. Once you have got good clustering algorithm, then you can use on unlabeled data. You know that now that whatever clustering method you are using is good enough because it is giving good score on known labels. Then you know that your method is good. It's good. It's creating good clusters. Then you can apply it on unseen, unlabeled data after that. That is fine. Okay, how to compare labeled data with cluster data? This one. So why is the actual data, actual label, and lab I'm calling this the labels. So this is the CLS dot labels. If you look at one of the contact hour slides, you'll see somewhere we are using these labels dot labels. Okay, so that is the cluster label that the clustering algorithm is giving. Okay, and then that you will compare with the actual labels, and then pairwise. So all these distances are pairwise, right? Adjusted rand index and all these things. Okay. Any doubts? If any doubts, please post in the chat box. Okay, we know we are new to the subject, so please ask theory in exam. Yeah, coding is very little in exam. Okay? Don't worry about coding part. Coding I have given you assignment, so that's all. So in exam, what you will get is mostly about numerical problems and theoretical problems. Okay, but very less coding. Even if there's some coding, you'll see that in it is like in midterm. Like it was like just fill up some code or complete some code, and you'll have available it's open book, so you'll have available your slides and all material is available to you. Okay, so but thing is you should take your calculators and all the exam, because now you have some logs and all that you have to calculate. Okay, so take your calculators. Any other question? Yes, you have to perform. You have to perform k-means. You have to perform hierarchical both. So actually, it seems like the classifier problem is easier than clustering. It seems to me. Okay, but it's up to you. So you perform both k-means and hierarchical clustering. Yes, both. But I think the only difference is just name. You just have to call a different function name. The remaining part is all same, whether it is classification or clustering, except the linkage. Try with single and complete. So if you've already done clustering, that's good. But you have to do both k-means and hierarchical, just like it is mentioned in the assignment. Okay. So in classification, you have to perform decision tree, in which decision tree has a lot of parameters to set. So you have to do a lot of in this decision tree. Whereas in SBC, there's less parameters, only C, capital C, that you have to try a few of them. You get a good score. In case of hierarchical clustering here, in case of clustering problem, the k-means doesn't have anything to set, only k. You can try for k from 2 onwards up to 20. I think I mentioned. The same thing you have to do in the hierarchical clustering, except linkage you have to add complete or single. I think I mentioned 2. Just check complete and single linkage. So these are the options which you have. Okay. So I think I have given you like 80% of the code is now given to you. The remaining 20% you have to fill up. Okay, so it's not find it too difficult. Some of you might be having some problem with this earlier. Now it is easy. Only thing you have to do is pre-processing. Okay, so in that also you have to can do a similar thing for all files. Do this thing and save them in a particular different folder. Okay, and different, just create different same kind of folders in a different path, and save your stemmed file in that hierarchy. Okay, and then later on use the new stemmed version of the files. Okay, so in SBC classifier of sklearn, if you just go to this, go to the page, the API, it has the C, capital C mentioned there. Okay, so try a few values. May try for example 0.1, then 1, 10, 100, like this. Among these only you will get good score, good value. One of the good scores will be among these 0.1, 1, 10, 100. Okay, so C value is not given in this example, but it is there in SBC set. Okay. So we may learn more about the C value and others in that page. In that web page, it is mentioned very clearly. So it's much better than I can explain here. So please just refer to that page, and you can also go to some online help because it's not very easy thing to do. Okay. So for linear, and also you have to set kernel as well linear. Okay, in SBC, you set kernel as linear. That is already given here. Yeah. So don't forget random state equal to 42. So in many places like decision trees and all, you have to set random state equal to 42 so that you get the same result every time. Otherwise, your result will keep on changing. So use this seed random state equal to some number. Okay. So broadly, what capital C does in SVM support vector machine is just it controls kind of the weighting, overrating and underweighting, how closely it should match the training data. Okay, so whether you can miss out a few examples or should exactly follow them, that's what it controls. So it is difficult to do people like me who don't have coding background. Okay, so that's why I've given you all these examples. Right now you have almost a full code. So should be able to score good marks in assignment, even if you just try to substitute some values here. Okay, so it should not be difficult now. So if the pre-processing part is not working for you, if not able to do that, you lose some marks. But this part is all available. You can still do that and good score. Right? You can get good score like I got here without any pre-processing. I got 94% accuracy. So I'm assuming that you should be able to get at least 94% accuracy in SVM when using SVC classifier. And for decision tree, at least 70% F1 score. Yeah, the slides will be uploaded by the Vision. Yeah, the slides will be uploaded. Okay. Okay. Thanks for the kind words. So I think we should stop here if you don't have any other question. Okay. So we'll have one review session next week. Okay. Okay. So thank you.